Alright, this video is going to be on implicit differentiation. So first, what is an implicit curve? An implicit curve is a curve where, you cannot necessarily solve for y. So I'm going to give you two examples. This first one is the equation of a circle, and you can solve for y here, but we are still going to use implicit differentiation on it because it makes the problem a little bit easier. So here, there is the y. We could isolate it, so we're going to say we can solve for y. But then we have other equations like x to the third plus y to the third equals xy squared, and that would be a little bit harder to solve for y. So, both of these forms are easier to find the derivative for if you use implicit differentiation as opposed to rules that we've learned in the past, okay? So it's easier to do it that way. So one thing, we want to recall some notation. So if I wanted to find the derivative of y, I would say that is y prime or dy dx. Those are two different types of notation that mean the same thing. And if I wanted to write the derivative of y, I could say d dx of y. So that's kind of like saying take the derivative d dx of y, right? And then once you do take the derivative of y, these are the things that you get. Okay, so we're going to go ahead and get started on some examples. The instructions are going to say find dy dx. And these instructions could have said find the derivative of y, they could have said differentiate the function, they could have said find the derivative of the function. It's all essentially the same. So here, for our first example, we're going to say x squared plus y squared equals 25. So we are talking about that circle that's centered at 0, 0 with a radius of 5. And the way that this works is we're going to take just the derivative of all the pieces involved. So the derivative of x squared is 2x. The derivative of y squared is 2y. And since y is some function, y is not just a letter on its own. We usually have like y equals something. Since y is some function, I don't know what the derivative of y is. It's probably not just a function like all by itself. It probably has things involved. So I'm going to say I have to multiply this by the derivative of y. So this is a chain rule problem. So I took the derivative of the outside function, which is y squared, and now I'm multiplying it by the derivative of the inside function, which is y. I just don't know what y would be when it was isolated. And that's why I'm not able to write what it would be. I just have to say dy dx. And then on the other side, the derivative of 25 is 0. So now in the problem, I just have to solve for dy dx, and then I have my answer. So I'm going to go ahead and start moving things away from dy dx so that I can isolate it. And that gives me 2y dy dx equals negative 2x. And then I'll go ahead and divide by 2y. And so dy dx equals, I can cancel out my 2's. I divide to make a 1. And so dy dx is negative x divided by y. And I was able to do that using implicit differentiation. Alright, for the second problem, we're going to do that other one that like truly requires this as a method, because you would have a very hard time isolating y in this problem. So again, we're just going to take the derivative of everything. So the derivative of x to the third is 3x squared. the derivative of y to the third I'm going to have to use the chain rule on, because if I were to isolate y, it would be some sort of function. So I'm going to say this is some sort of function raised to the third power. So the chain rule tells me to do 3y squared. So I left the inside function on the inside. And then I need to multiply that by the derivative of the inside function, whatever it would happen to be. Right? So I took the derivative of each of those. On the right side of the equation, we have the chain rule, or not the chain rule, we have the product rule happening. So I've got first multiplied by the derivative of the second. So the outside function would tell me that the derivative is 2y. Y is the inside function. So then I need to multiply by the derivative of y. So the first multiplied by the derivative of the second plus the second multiplied by the derivative of the first. Okay. So when I do these, I like to clean things up a little bit. It helps me to think through the problem more easily. And again, just like in the previous problem, our goal is to isolate dy dx, which is kind of tricky since we have it in two places. So either way, if I'm trying to isolate something, I definitely want all of that something on one side of the equation. So I'm going to go ahead and get these two on the same side. So I'm going to go ahead and subtract the 3x squared to the opposite side since it did not have the dy dx. And then, so that's gone. And then I'm going to take this and I'm going to move it over here. All right, so at this point, I have negative 2xy dy dx and a positive 3y squared dy dx, and that equals a negative 3x squared plus y squared. And it's okay if you wrote it in a different order than I did. I just alphabetized it, basically. Now, here is the trick to isolating dy dx when you have it in two spots like that. If you notice, it's in both of them, and so that means it's kind of like a GCF, so we can take it out. And then if you take it out of this one, that leaves you with negative 2xy. If you take it out of that one, that leaves 3y squared. And at this point, we can isolate dy dx by dividing by all that stuff in the parentheses. And so that's the answer. I have dy dx equals negative 3x squared plus y squared divided by negative 2xy plus 3y squared. And there's our very complicated answer. Okay, for the next example, we're going to do kind of a more interesting problem where there's some application involved. So this says to find the equation of the tangent line to the circle. And it's the circle we dealt with before, which was x squared plus y squared equals 25 at the point 3, 4. So to find the equation of the tangent line at a specific point, we need to know what the derivative at that point is. So we already found the derivative in the first example. So from number 1, we knew that the derivative for that circle is negative x divided by y. So if we want to find the instantaneous rate of change, or the instantaneous slope at that point, we just need to take 3 and plug it in for x, and 4 and plug it in for y. And so that gives us negative 3/4. Now we can go ahead and use the formula, the point slope formula, to write the equation of a line. So I should have y minus 4 equals negative 3/4 x minus 3. All right, here's another example. We're going to say that we want to differentiate sine of xy, and that equals 2x plus 5. So again, it would be very difficult for us to isolate this equation and make it a function where y equals something in terms of x. So we're going to go ahead and use implicit differentiation on this. So for the left side, that's a chain rule problem. So I'm going to say the derivative of the outside function is cos, and I keep the inside the same. And then I multiply that by the derivative of the inside function, and the inside function has a product rule. So I'm going to say I've got the first times the derivative of the second plus the second times the derivative of the first. And hopefully you're noticing that basically anytime we do something with the derivative of y, we just have to put dy dx next to it. Okay, and the reason for that is because of the chain rule. If that is confusing, if you didn't understand it from the video, then let me know in class and I will definitely talk more about that. And then on the right side, the derivative of 2x plus 5 is just 2. Okay, so at this point, again, we have to solve for dy dx. So I'm going to clean things up a little bit. Not equals times x dy dx plus y. Yeah, equals 2. So we are moving stuff away from dy dx. So the first thing I can move away is that cos. So that gives me x dy dx plus y equals, now 2 divided by cos is actually the same as secant, right? This is kind of like saying 2 times 1 over cos. And so that would be 2 secant of xy. So that makes it a little bit more simple just because I'm not dealing with a fraction anymore. And then I can go ahead and subtract my y over. And then I can go ahead and divide the x over. So I'm going to say that dy dx is 2 secant of xy minus y, all divided by x. All right, we have one last example, and I thought about whether or not I wanted this one on the video, and I think I do only because I want it to sink in overnight. I want you to absorb it for a little while. So we're going to go ahead and do this one. It says find, and I do not know how to say this out loud, so this notation, like d squared y divided by dx squared, I have no idea if that's how they say it, they're asking you to find the second derivative, but to do it implicitly. So find the second derivative when x to the fourth plus y to the fourth equals 16. And we're going to do this in terms of x and y. And that's how we've done all the problems, so that's not any different. All of these answers are in terms of x and y, so that's no surprise. So first, we have to find the first derivative. So I'm going to go ahead and do that. So 4 gets brought down to the front. 4x to the third plus the derivative of y, so that'd be 4y to the third, and then we've got the chain rule part of this, equals the derivative of 16 is 0. So for me to finish solving my first derivative, I have to get dy dx alone. So I'll go ahead and subtract the 4x to the third to the other side. So it gives me 4y to the third, dy dx equals negative 4x to the third. And then I will go ahead and divide the 4y to the third over. So dy dx equals negative 4x to the third divided by 4y to the third. And the 4's cancel. They divide to make a 1. And so I would say that my derivative is negative x to the third divided by y to the third. So that is my first derivative. Now, for me to do my second derivative, I just need to take the derivative of that. All right, so if you look at that, I'm going to start a new sheet. Please don't be nervous. So to take the derivative of that, that's a quotient rule problem. All right, so I'm going to say the second derivative, however you pronounce that thing, is going to be low d high So the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Whew. Okay, I'm going to clean it up a little bit. So on the top I've got negative 3x squared y to the third plus 3x to the third y squared dy dx divided by y to the sixth. Okay, now we are not solving for dy dx because that represents the first derivative, not the second derivative, and we already have the second derivative isolated over here. So that means we've already found it. This is the second derivative. Right now, it's in terms of the x's and the y's, and it's also in terms of the first derivative, which is the confusing part about this. So what we're going to do next, and this is kind of a trick to doing these, is we're going to take dy dx right here, and we know what dy dx equals. It's this. And we're going to take this, and we're going to substitute it in for that dy dx right there. Okay? So I'm going to go ahead and say I'm not using that. I'm actually multiplying this. Instead of saying multiplied by dy dx, I'm multiplying it by negative x to the third, y to the third, because that's what that actually equaled. Okay, stay with me. So now I'm going to simplify a little bit. I can see that I have a y squared being multiplied by this, and over here I can see I'm dividing by something. So I'm going to go ahead and say multiply by y squared and divide by y squared, and that leaves a 1 left over. Actually, I can multiply those. 3x to the third multiplied by negative x to the third would be negative 3x to the sixth. And this part right here is being divided by y. And then underneath this fraction, we have y to the sixth. So this is a complex fraction now, and the only reason I say that is because I got this y right here that I don't like. So I'm going to go ahead and multiply this equation by y over y. So when I take this y and I multiply it all the way over here, that gives me negative 3x squared y to the fourth. When I take it and multiply it right here, it cancels with the y on the bottom, and I get negative 3x to the sixth. And that's divided by y to the seventh. Okay. So if you're looking at the top, you might notice there's a GCF in this problem. So I can see that negative 3 could divide out. And I can see that there's an x squared in both of those pieces. So I can go ahead and divide that out. And if you do that, you're left with y to the fourth plus, if I divide out the negative 3 and the x squared, I get x to the fourth. And inside the parentheses right here, x to the fourth plus y to the fourth was actually the very original function. If you look in the very beginning of the problem, we said x to the fourth plus y to the fourth is 16. So I can take this and say, nope, I'm going to put 16 right in there. This is where you guys are like, Ms. Rice, I would never do this. I would never see that. The answer is, I might not either. It's just a lot of math takes just lots and lots and lots and lots of practice so that you do it enough times so that you start to recognize these sorts of things. So now that I've seen it, I probably would be more apt to recognize it. And hopefully as you guys do more practice of these, that will be the same for you. So negative 3 times 16 is negative 48 x squared divided by y to the seventh. And that, my friends, is our second derivative. I guess I could put that.